I don't always listen to podcasts, but when I do, I listen to STEM Talk, interviewing the most interesting people in the world of science and technology. Stay curious, my friends.
Welcome to STEM Talk.
STEM Talk.
STEM Talk.
STEM Talk.
STEM Talk. STEM Talk.
Welcome to STEM Talk, where we introduce you to fascinating people who passionately inhabit the scientific and technical frontiers of our society. So today we have a terrific interview with Dr. Michael Turner, who will discuss gravity waves, the effort to fund and build the LIGO instrument that actually did detect a gravity wave, and much else.
Michael was the assistant director at the National Science Foundation, responsible for the development and funding of LIGO. And without Michael, it's not clear there would have been a LIGO.
And of course, this topic is of great current interest, as it was recently announced that on September 15th in 2015, LIGO had indeed detected a gravity wave generated during the final fraction of a second of the merger of two black holes. 100 years ago, Einstein predicted the existence of gravity waves. However, until now, they had never been observed. So what exactly is a gravity wave?
Well, our best description of gravity comes from Einstein's general theory of relativity, which describes it not as a force, as is commonly thought, but as a consequence of the curvature of space-time caused by the uneven distribution of mass. For example, the sun significantly warps space-time in a way analogous to a bowling ball sitting on a swimming pool cover. Gravity waves are ripples in the fabric of space-time caused by a cataclysmic event. Like the ripples in a pond caused by a rock dropped into it. Of course, this is only analogy. The detection of gravity waves confirms a major prediction of Einstein's general theory of relativity and opens a new window into the cosmos.
And so this detection occurred on September 14th, 2015 at 5:51 a.m. Eastern Daylight Time by both of the twin laser interferometer gravitational-wave observatory detectors, also known as LIGO detectors. One is located in Livingston, Louisiana, and the other in Hanford, Washington. The LIGO observatories are funded by the National Science Foundation and were conceived, built, and are operated by a large team of collaborators led by CalTech and MIT. These LIGO observatories are amazing feats of engineering in themselves, able to detect ripples in space-time thousands of times smaller than a proton.
On the 16th of February 2016, the New York Times editorial board referred to the detection as the chirp heard across the universe. Let's hear that chirp now. Wow, that is the sound created by the collision of two black holes a billion light years away. This will be an interesting interview indeed.
Absolutely. But before we get to today's interview, we have some housekeeping to take care of. First, we really appreciate all of you who have subscribed to STEM Talk, and we especially appreciate all the wonderful 5-star reviews piling up on iTunes.
As we announced earlier, the Double Secret Selection Committee is continually and carefully reviewing the iTunes reviews with an eye toward selecting the best and perhaps the most pithy among them to read on the air, so to speak, if a podcast can even be said to have air.
And if you hear your review read on STEM Talk, just contact us at stemtalk@ihmc.us to claim your official STEM Talk shirt. Our first winner is a review posted by someone called Best Nickname Ever. Nickname? That's a little odd, but perhaps it's a typo, or maybe they meant nickname. In any case, thanks Nickname for the great review, and here it is. Quote unquote, IHMC, Ken Ford and friends are kicking down walls between the smartest thinkers engaged in solving problems and extending human capacity. I'll never miss a podcast. Check out their lectures too.
Wow, that's a good one. And here's another iTunes review by someone writing under the name Baba La Poet. What a great name. This person writes, the individuals interviewed are articulate, knowledgeable, and able to clearly convey information about their respective fields. The interviewers and the Institute are to be congratulated for putting this series together for my and others' enjoyment. Thank you.
And thank you, Baba La Poet, and all of the other excellent reviewers and subscribers who listen to STEM Talk. Okay, now on to today's interview. Michael Turner is a theoretical cosmologist who coined the term dark energy in 1998 and is the Rauner Distinguished Service Professor at the University of Chicago. In addition, he served as the Assistant Director for Mathematical and Physical Sciences for the U.S. National Science Foundation from 2003 to 2006. More recently, in 2013, Dr. Turner was elected as the President of the American Physical Society.
Michael is the recipient of too many awards and honors to recite, so we won't. But suffice it to say that he has, through his own research and through his substantial leadership, greatly shaped the scientific landscape, especially in physics and cosmology. His research focuses on the earliest moments of creation, what is sometimes referred to as the Big Bang, and he has made contributions to inflationary cosmology, dark matter, and dark energy.
STEM Talk.
STEM Talk.
Well, thank you so much for joining us. I know you've got a lot going on, so...
Happy to be here.
So, Michael, tell us a little bit more about your background from childhood on and how it influenced your development as a scientist.
Oh, my goodness, from childhood on. That's a long time ago. Well, I guess I was always a curious kid. And the path to becoming a scientist probably started out by tinkering with electronics and becoming a ham radio operator. And so I built stuff and talked to people all over the world and, almost electrocuted myself several times and met really interesting people. I met, this is way back when, I met a young man who had just emigrated to the U.S. from Germany, and he was an engineer, and he was an engineer's engineer. And so I was probably in high school, and I started hanging out with him at his house, and we built stuff, and I really enjoyed doing this. And parallel to this was school. And so I like to say that I went to the best schools that money could buy in the 60s, which was the public schools in California.
Yeah.
And I had fantastic teachers, and there were three of them that took this curious young man and helped, mischievous might also be in there, and a chemistry teacher, a math teacher, and a physics teacher. And the chemistry teacher helped my friends and I buy chemicals to build explosives. We didn't get stuff that was too explosive, and we launched gas-filled balloons and created UFOs over Los Angeles. I don't know if anyone ever saw them.
That's awesome.
And the math teacher inspired a love of mathematics in me, and also a love of the state of South Dakota. So she was from South Dakota, and she was such a wonderful teacher that to this day, anything South Dakota I love. And she inspired me in mathematics. And a very poignant moment was when I discovered that while I really loved mathematics, I liked the things that it could do. And so the physics teacher, who I'll bring into the story, got me to stand in front of his blackboard with a sign that says, "Math is but a tool." And I had found my real passion with physics. And this physics teacher, among other things, took me and a couple of my friends to the Monday night lectures at CalTech. And oh my goodness, this was before permission forms, before seat belts, something that you could never do today. And it just opened this world of stuff that was going on at the forefront of science. And I fell in love with CalTech. And I decided that was where I wanted to go to school. It is where I went to school. I applied to 3 places, Stanford, CalTech, and MIT. And my mother wanted me to go to Stanford to become more well-rounded. My father wanted me to go to MIT because the people he knew and respected the most were engineers, and MIT is an engineering school.
Mm-hmm.
And but CalTech was where I wanted to go. And so I got one booster in this. Well, first of all, my parents would have let me go there anyway, but my mother was working at the RAND Corporation and went and talked to the head of the physics department there, a guy named Dick Ladder. And he was a CalTech graduate, and he explained to my mother that if I had been admitted to CalTech, that is where I should go. So I had a great time at CalTech. I continued to be mischievous, and a couple of professors there really watched out for me and made sure I graduated, and then went on to Stanford, where I did my Ph.D. I went on to Stanford at the advice of Richard Feynman, which is kind of an interesting story. Great scientist, the world's most selfish person, in a positive way.
Yeah.
He was only interested in what he was interested in.
Yeah.
So when I asked him for advice about where I should go to graduate school, what he told me is where he would go. But he didn't tell me that. I mean, he just didn't, but it was great. Stanford was the right place to be.
Mm-hmm.
And then after Stanford, I went on to Chicago, and I guess I'm out of my childhood. And I've been at Chicago. I came to Chicago in 1978 as an Enrico Fermi Fellow. And having never lived outside of California, my goal was to get back to California as soon as possible. And but Chicago is such a great place that even given many opportunities to get back to California, this is the place I belong. So I've been happily in Chicago ever since.
Yeah, it's a great place to be, and it sounds like you've had a lot of mentors who have kind of guided you along the way.
The person who brought me to the University of Chicago was David Schramm, a very famous scientist who died in a plane crash in 1997. And he would become my mentor. And I met him at CalTech in the gym.
Oh, wow.
And it was a very funny way to meet him because CalTech's a very small place and athletics don't play a very important role, but we were required to take PE. And he was the assistant wrestling coach. And I had such pity for the wrestling coach. Oh my God, you're the wrestling coach at CalTech. And I don't even know what I had for the assistant wrestling coach. And here was this guy who looked like a gym rat. And I could only imagine, oh my God, if the lowest position in life is the wrestling coach at CalTech, what is assistant wrestling coach? Well, it turned out that David Schramm, this was a graduate student at CalTech who just loved the gym, a fantastic scientist. But when he was at MIT, he was a wrestling champion and an alternate to, I forget what Olympics, 1964 Olympics or something. So I met him there, didn't really meet him. And later I discovered, when I was becoming scientifically aware by the time I was at Stanford and a graduate student of this David Schramm person, is that, oh my God, that's the guy I had met at CalTech.
That's funny.
He called me up. I got a couple of job offers when I finished at Stanford. One was from Harvard, one was from CalTech. Sorry, one was from Harvard and one was from Chicago. And Dave Schramm called up. And all I remember of the call was his exuberance. Come to Chicago, you'll do great things. And the call from Harvard was a bit more complicated. It was completely above my head. It was, we know that you were not Chicago's first choice, but you're Harvard's first choice. And we know that Dave Schramm is a better salesman. And that's all I remember of the call. And, oh my God, I had 2 job offers. Yeah. I mean, what does it mean I wasn't their first choice? So I went to Chicago, and David became not only my friend, but my mentor, and curved the path of my career a little bit from astrophysics and gravitational waves to early universe cosmology, and was my mentor until he died in 1997. But he was indeed a wrestler, and an amazing competitor. I'm pretty competitive. We played racquetball, and I became well known around the astronomy department at the University of Chicago because I played racquetball with Dave for a couple of years without getting an injury, and everyone else who played with him got an injury. Not because he was just an aggressive player, but what was amazing was after about 6 months, I had not taken a single match from him. And after about 6 months, you have to trust me, objectively speaking, I felt I was the better player, and I was often ahead. And he was such a competitor that, there I am, I'm ahead. I'm within inches of beating him, and I could just feel his competitive juices take over. And I remember one time we ran in a 10K race in Aspen, and neither one of us were in very good shape that summer, and I was pacing myself, and he went out ahead, and I thought he's never going to keep up that pace. And I got at kind of the 8-kilometer mark, and I said, if I haven't seen him yet, I'm going to lose, because even if I catch him at 8 kilometers, and even if he's crawling, he will still. But we had many, many good times together, and his toughness, his and his enthusiasm for science are things that I take with me to this day. So thank you for reminding me of David.
That's great. It sounds like his spirit still lives on with you as well as a researcher and also as a friend.
Yeah, and at the University of Chicago, he really changed the course of cosmology and astronomy at the University of Chicago, and his loss was a very, very big one. And we have many things here named after him.
STEM Talk is an educational service of the Florida Institute for Human and Machine Cognition, a not-for-profit research lab pioneering groundbreaking technologies aimed at leveraging and extending human cognition, perception, locomotion, and resilience.
I also hear that you're passionate about cycling. Do you cycle on a regular basis in Chicago, or is that a good place to ride? Are you able to get out and get some good riding in there?
I've gone through various phases of cycling in my life, and I'm in an active phase right now where I really, really love it and am passionate for it. Chicago is not the world's best place to ride, but it's a good place to train. And so my favorite thing riding in Chicago is I'll be out riding later today because the weather permits. And even during the winter, as long as it's warmer than 20 degrees, I'll go out riding. And but what's great about Chicago is it toughens you up. And then what I really like is riding in the hills. And so I'll go out to California and ride with my friends. And there I've been, 3 months on the flatlands of Chicago, and I go in the hills with them, and I kick their butts because, as they say, I'm Chi-Town tough.
I like that. So now I'm going to kind of switch over from personal to talking a little bit about science. So you've called the discovery of gravitational waves the last big prediction of the theory of relativity. Can you explain this statement?
Yeah, so Einstein's theory of general relativity had some big predictions. The one that probably everyone has heard about is the bending of starlight. And that was the first big success. And that one, Sir Arthur Eddington led an expedition in 1919 that verified the prediction. And that put Einstein on the map, front page of the New York Times. And I won't go through all the other predictions, but the fourth major prediction was gravitational waves. And that was a very interesting one because first of all, Einstein pointed out that there should be such things in his theory. And then, he did a John Kerry on us and said, well, but I don't think they're real. And there was great debate on whether gravitational waves were just an artifact, a mathematical artifact, or the real thing. And that didn't get settled till 1960. So, his theory is 100 years old last year. So that was a long time for it to get settled. And then actually detecting them is extremely hard. And of course, last February, the LIGO collaboration announced evidence for the direct detection of gravitational waves. And so I would say that was the last big prediction. I mean, there are plenty of other predictions, but this was a biggie. Are there waves just like there are electromagnetic waves? And yes, indeed, they are. Mm-hmm. And so this really opened up a new window on the universe. And I like to call this event that happened about a month ago a Galileo moment, where, 400 years ago, Galileo turned the telescopes to the sky and opened our eyes to the universe. And now we have this new window on the universe.
Yeah, and you've quoted Galileo and said that this discovery has made measurable what is not so. So how did they do this?
So that's really the stunner in all of this, is that there's many people consider Galileo the father of modern science. And one of the reasons they do is that he talked about making measurements to test theories. And there's this quote of his that I find absolutely wonderful. Measure that which is measurable and make measurable that which is not measurable. Mm-hmm. And so let's talk about what the LIGO team did. So these two black holes about 1 billion light years away shook up space-time. I mean, if you were there, you would not be pleased to be there. You would have gotten stretched all over the place. So really big stretches of the fabric of space-time. Those waves propagated out in the universe, and they manifested themselves here on Earth as a jiggle that would cause two mirrors 4 kilometers apart. I'll tell you why we're talking about two mirrors 4 kilometers apart, to change their separation by 1,000th the diameter of a proton. So I won't even give that in centimeters. I think everybody gets that that's really small.
Really small, yeah.
Tiny distance over 4 kilometers. And so this was the challenge in building a gravitational wave detector, is to be able to measure such a small distance change over such a large distance. And so, I mean, I think I said in this same essay that Galileo would be smiling. The idea that you could make, obviously, what at first blush, what they were trying to measure was unmeasurable, and they made it measurable by using a technique that was invented by Albert Michelson, the first U.S. Nobel Prize winner and a professor at the University of Chicago for a number of years, using an interferometer, using the wavelength of light, which we think of as being very, very small, and it is, but using it in a very clever way to be able to measure such a tiny distance with great precision. And so I think this was just an amazing accomplishment that took, you can put 40 years, 50 years. I alluded to when I was in graduate school, my Ph.D. thesis was on gravitational waves, and that was written in 1978. And people were saying, Kip Thorne, one of the giants in the field, was saying, the detection of gravitational waves is around the corner. And of course, I interpreted that to be the 1980s. The corner was a bit longer than most people thought, and it took just an amazing effort of scientists, and the National Science Foundation should get a shout out here. Mm-hmm. They recognize this as something, a very, very lofty goal, a moonshot, if you will, worthy to do, and to stick with it through the ups and downs. And in 2016, they achieved what Galileo said we should do, is make measurable that which is not currently measurable.
It's fascinating. So tell us more about the scientists that played the most critical roles in developing LIGO over the years. So you mentioned Albert Michelson. Who else was involved?
So Albert Michelson, I should clarify a little bit. Of course, can't remember when he died, but he did his most important work around the turn of the 20th century, but he invented this technique called the Michelson interferometer, which we still use today, and it's a way to measure very small distances. So we can anchor it there. The first person who actually tried to measure gravitational waves was a gentleman named Joe Weber, an extraordinarily creative scientist. And in the 1960s, he built a bar. So a gravitational wave, his idea was that gravitational wave would come, and it would cause the two ends of the bars to change separation and cause the bar to ring. Mm-hmm. Not very loud, so you have to put a sensitive detector. And so he built these Weber bars and thought he had made some detections and hadn't, and probably stuck with his claim too long, but he really was a genius at all of this. And the interesting thing is the modern LIGO uses lasers and interferometry, that is interfering using the wave property of light and interference to measure small distances. He had a graduate student named Bob Forward who worked at Hughes Research Lab. And when Forward finished his PhD thesis, Weber told him, you go back to Hughes Research Lab and build an interferometer to detect gravity waves. And indeed he did. He built the first one. And that was in the late 60s, early 70s. And then CalTech and MIT really thought this was a worthy goal and built much larger instruments, 40 meters in length. The larger the instrument, the more sensitive it is. And there, the people who come into play are Ray Weiss at MIT, who I would call him the experimenter's experimentalist. Someone who can just loves to do experiments and make measurements. And he got the gravity wave bug at MIT. And Kip Thorne, who was a theorist, but really wanted to see gravity waves detected and the new window being open at CalTech, my alma mater. CalTech does great, small school that does great things, hired an experimentalist from Glasgow named Ron Drever. And actually then Chicago comes into play. The very first graduate student whose committee I sat on, Stan Whitcomb, got a job offer from CalTech and asked me if he should take it. And I said, this is not for the faint-hearted, but this is a really, this is something really important. So he went to CalTech and worked with Ron Drever. And then CalTech and MIT got together and said, okay, we've proved the principle that you can build one of these, but 40 meters is not enough. It has to be 4 kilometers.
Wow.
And 100 times bigger. I think that's right, 100 times bigger. They went to the National Science Foundation, and now comes the NSF playing a role. This is the kind of stuff that NSF does really, really well, sort of throwing deep. So a proposal went to NSF to build this thing. And the story is absolutely wonderful because for these throw deep ideas, these really big ideas, it's a really big, important idea if half the people say, this is the most important thing we can do, and the other half say, this is crazy, don't waste your money.
Yeah.
And so the astronomers hated LIGO. They hated the O. So it's Laser Interferometer Gravity Wave Observatory. So they said, we do observatories. You're doing a physics experiment. If you would call it LIGO, Laser Interferometer Gravity Wave Experiment. Anyway, NSF looked at this and said, this is a lofty goal. Let's do it. And so that was in 1990. I forget if it was 2 or 4, in the mid 1990s. And NSF tried to do this, a big project, CalTech and MIT. And this is where my other mentor, my undergraduate mentor, Barry Barish, comes into play. He was a high energy experimentalist, and the only scientists really used to doing big projects were high energy physicists. And this was a big project, and it was not going well. And so CalTech asked Barry Barish to come in and take over the project. And the project, if we use an airplane analogy, this was a 747 heading towards the Earth, a few hundred meters above the ground. And he pulled the airplane out of the dive and got the project going. And they achieved, in fact, this was such a lofty goal that NSF said, we're going to do this in 2 phases. Phase 1, initial LIGO, where you're going to show that you can scale up from 40 meters to 4 kilometers. And we realized that once you do that, your chances of detecting gravity waves are kind of 50-50. Because never having seen a gravity wave before, you don't really know what's out there. And NSF said, if you succeed in doing that, then we will let you improve the sensitivity by another factor of 10 or 15. And then you're guaranteed to see something based on all the estimates. And so I come into the picture again. I'm a cosmologist by now. I'm no longer doing gravity waves, but I took a 3-year stint at NSF in charge of math and physical sciences. And lo and behold, what's on my desk? But it's time for advanced LIGO. They've demonstrated the initial LIGO, and they now want to scale up. And I had to make a recommendation to the director. Do we do this? Do we not do it? And then sell it to the National Science Board. And that turned out to be, I thought it was going to be, as they say, a slam dunk. But it turns out that there were still people bitter over the original, the people who thought that NSF shouldn't have done LIGO in the first place were arguing, and don't waste any more money.
Right.
And so I first had to convince not one director, but 2 directors, because NSF had a change in director, Rita Caldwell and then Arden Bement. And then the science board, because the science board is the group that oversees it and, make sure that NSF is spending its money wisely on these throw deep projects. And so that was really fun to be involved in convincing the science board, people who are very intelligent and are very well connected in the community. So they're hearing conflicting things about doing it. And we took them down to the Livingston site and showed them what had been done. And it took, more than a year for the board to decide. But they stuck with it. And I think NSF is pretty happy it stuck with it, because this is really an example of, I don't think and this is not meant to criticize any other agency, but I don't think this kind of novel, throw deep, never been done before project could be done by any other agency. And it was not an easy ride. There were ups and downs along the way, and NSF really stuck with it, and CalTech and MIT stuck with it, and Ray Weiss was there from the mid-90s. He was at the press conference was wonderful being at the press conference, seeing Ray Weiss give a physics lecture at the press conference, explaining how all this works. And this is absolutely wonderful. And the other thing that I think is going to happen is that this happened during their engineering run. They're not even at full sensitivity. And so I think the other thing that's going to happen is LIGO is going to earn its O. That is, become an observatory. Because if it got one event that quickly, it's going to have tens of events, and it'll be a real observatory. And the dreams of people like Kip Thorne and others are going to come true. This is going to be a new window on the universe.
I don't always listen to podcasts, but when I do, I listen to STEM Talk, interviewing the most interesting people in the world of science and technology. Stay curious, my friends.
Yeah, this discovery itself, and also just the observatory and the creation of LIGO is clearly an example of what is sometimes referred to as big science. And in a project of this scope and ambition, there are ups and downs, like you were talking about Barry Barish, kind of pulling the project out of a nosedive, and all the ups and downs. So it's really fascinating to hear about the history that was involved, and it wasn't just as straightforward. We're going to make this thing happen, and it all goes according to plan.
Yeah, I mean that's one of the people give various definitions of science, and one of them that I like is adventure with a purpose.
That's great.
And it really was an adventure. And one thing I try to convey to my students is we don't always get it right the first time. In fact, actually, I should be a little more honest. We rarely get it right the first time. And big science is something that's relatively new, post-World War II. It's hard to define when big science started, but there are a lot of big science projects that, not so many that have really failed, but that have had, everybody knows about the Hubble and the mirror that wasn't quite right. And the James Webb Space Telescope had cost more than people thought. And these things, I always harken back to John Kennedy's quote about going to the moon. And he talked about going to the moon is really hard. That's why we're doing it.
Science is just a different form of exploration. So it's really interesting to hear the whole history and the whole context of LIGO. And you were talking about when you were in the role of assistant director at NSF, and from what I understand, at that same time, IHMC's director Ken Ford was also serving on the National Science Board. And he was chairing the committee on programs and plans. And so it sounds like you two had numerous interactions during that time regarding the funding and support for LIGO.
The Science Board, you're absolutely right. Ken Ford was one of these wise people on the Science Board who, and wise in the best sense of the word, is that they want to make sure that they're the adult supervision in the room. Scientists can be very exuberant, like, 2-year-old children. I want this now. And so the board had to do due diligence. And, Ken is an expert in computer science, and but not in gravitational wave physics. And, people tell him, some people were telling him this is really a dumb idea, and other people are saying, this is brilliant. And so the interactions with Ken and others on the board, some were more skeptical than Ken, and I remember the final presentation when we had gone through CPP, Committee on Programs and Plans, to the full board for the final vote. And, once you're there, you're pretty much sure, once you've made it through the committee, you're pretty much sure it's going to go okay, because the committee is really doing they really study it very carefully, and then it comes to the full board. And that presentation was wonderful. We had a rich conversation. I remember one of the board members saying, "Can you guarantee this is going to work?" And I said, "No. This is science. We're at the frontier." And he said, one of the issues is, and it comes back to your very first question, do gravity waves really exist? And I said, that I'm 99% sure on. And he said, well, how can you be so sure? And I said, I'm a theorist. They have to be out there. And actually, we had some indirect evidence from a binary of two neutron stars whose orbit was decaying, was changing due to the emission of gravitational waves. But it was a wonderful, I wish I had a video of that, because I worked really hard on that presentation. The board had worked really hard on doing its due diligence. There was a lot of good give and take with people asking hard questions, and I didn't give stale answers. When somebody said, "Can you guarantee it would work?" I was thinking, I should just be honest. When in doubt, just be honest. Mm-hmm. No, I can't guarantee it'll work. But I do think we should do it, and I do think that this team has achieved something remarkable so far, and there is good reason to believe they can get that last factor of 10 or 15 in sensitivity. And if they do, there is even better reason to believe that they will detect something. And so I think the whole interaction, the 3 years I spent at NSF, I interacted with, I guess the board meets 6 times a year. And so I really got to know Ken and others. And these people really, we're doing a service to the country in making sure not only that we spend the money wisely, making sure that we spend the money wisely, but in 2 ways. You can spend it wisely by investing in things that will always work. But if you did that, NSF has a budget, I can't remember if it's $7 or $8 billion a year. For $7 or $8 billion a year, you need some deep throws in there every once in a while, right? I mean, you need to take some risks, some risks that aren't just crazy risks, but are calculated risks that will really advance things big time. Because if all you're doing is conservative stuff, we'll just do more of the same. That's not why we're investing the money in NSF. We're investing the money in NSF for those really big advances. And so the board had to have people on it like Ken who were wise enough to see, okay, we can't just do crazy stuff, but if we do all this boring guaranteed stuff, we're also not serving the nation well.
Yeah, absolutely. And what's interesting to me is coming out of all this, so, we've talked about NSF and we've talked about the National Science Board, and you've noted that science is collaborative and it's very much an international effort. You've talked about these people who have contributed to, the development of LIGO over the years, and they're not just U.S. based. So to what extent is this discovery an American success?
So that's a fun part. In this editorial I wrote in Science Magazine, you only have a limited number of words, but I did spend some of the words saying that this is an example where we as Americans can be very proud. So we pioneered this area. We made all the early investments. It's now very international. So, for example, the Europeans have something similar to LIGO called Virgo, and they are in the midst of upgrading it. So Virgo was not running on September 14th when this first event was recorded. The Japanese are making big investments, the Germans, the UK, but I think we can, we really led. And in this more flatter and more collaborative world, I think there's still a place for national pride and focus and competition. Competition's a good thing. And countries, we're not going to be able to dominate or win in every area, but I'll give you an example. So Japan, of course, is a major world power, but smaller than the U.S. And in high-energy physics, Japan had a decision to make. Should we try to compete with the U.S. and Europe to build the biggest accelerator? And for a while they did, and they decided that's not a really good strategy. Let's find a really important problem where we can be the lead. And so Japan focused on neutrinos. And 3 Nobel Prizes later, they're pretty happy they did. And so we chose to focus on gravity waves. And so I think this world that we're getting used to, where it's not only global and collaborative, it's competitive and cooperative. And just because things are collaborative and cooperative doesn't mean there won't be competition and there won't be leadership. And so finding our way in that world is really important. We're a great nation, and for 50 years we dominated in science. That's not going to happen anymore. But we do want to lead, and we do want to be proud of the discoveries that we led, and this is one of them.
Absolutely. So, what are the next steps in the aftermath of this discovery?
So the next thing that's really exciting, we may have to wait another 6 months, is, so as I mentioned earlier, this was an engineering run. That they weren't even trying to do science, but the signal was so loud that they, in fact, they didn't really have a protocol for what to do, but they couldn't ignore it. And so they studied it and convinced themselves it was real. They are now analyzing their first science run. And it was, I'm trying to remember, I think it was a 3-month science run. And they're still not at full sensitivity, but they now have 3 months of data that right now they're analyzing. And of course, they're also, they haven't achieved that full increase in sensitivity, and so they're going to do that. So I think what's ahead is earning the O, getting other events. And a year from now, Virgo will be done with their upgrades, and so we'll have a European detector. So that'll be exciting. The other thing that was a bit of a disappointment is that about 10 years ago, there was great excitement to put a gravity wave detector in space called LISA, Laser Interferometer Space Antenna. And it was going to be a collaborative project between the US and the European, between NASA and the European Space Agency. And due to complications on both sides, the project didn't go forward. And coincidentally, what's really wonderful is that just as both sides were realizing maybe it's the time to do LISA again, came this detection. And so I think LISA will have new energy. And what's exciting about LISA is just like the electromagnetic spectrum, so we have light of different wavelengths. We have really long wavelengths, radio waves, really short wavelengths, X-ray, gamma ray. Same is true with gravitational waves. And the waves of really long wavelength, low frequencies, can't be detected on Earth because the Earth is very noisy. And I really mean the Earth. I don't mean people on it. I mean seismic activity on Earth. And so to really reach the sensitivities you need to look at the universe, you need to go to space. It's not unlike needing to go to space to look for X-rays, because X-rays don't penetrate the atmosphere. So for the same reason, you need to go to space. And LISA, there's a number of things that it can see. So these black holes that LIGO saw were relatively modest in size, about 30 times the mass of the sun. LISA's exciting black hole target are the supermassive black holes at the centers of galaxies, the ones that are 1 million solar masses, and the symphony of the galaxy. So there are a lot of, in fact, this is what I did my thesis on, there are a lot of binary stars in our galaxies, and as these stars evolve, they eventually get close together, and when they get really close together, they end their life emitting gravitational waves. And so we'll be able to hear the galaxy, hear these binary stars in the galaxy with LISA. And of course, the most exciting thing, scientists love to say this, and the funding agencies don't like to hear it. The most exciting thing is the thing we haven't thought of. And if history is any guide, there will be wonderful discoveries that take us in new directions when we open up a new window on the universe.
Yeah, well, it's very exciting times ahead, and I really appreciate you, giving us some input into all that. Michael, you've visited IHMC on several occasions, and you've given really good, excellent lectures, and actually somewhat mind-boggling lectures when you visited here. And we noted this morning that your IHMC talks actually have over 20,000 views, so that was pretty impressive.
That's great.
Yeah,
nice to hear.
Yeah, disseminating the information appropriately. So, but we all look forward to your next visit and lecture, and I want to thank you so much for taking the time to talk with us today.
You're very welcome.
Yeah, thank you.
Okay, bye-bye.
STEM Talk.
STEM Talk.
STEM Talk.
STEM Talk. STEM Talk.
Wow, what an interesting discussion. That was so cool, and it was so great to talk to Dr. Michael Turner about the backstory on the road to the detection of gravity waves. In his role at NSF, Michael was intimately involved in the sometimes messy big science sausage that was being made. So Michael will be returning to STEM Talk in the near future to discuss some of the most mysterious aspects of our emerging understanding of the universe, dark energy and dark matter.
Also, as the detection of gravity waves is among the most significant scientific discoveries of recent decades, we will have at least one more episode on this topic. In fact, in the near future, Dr. Barry Barish will be our guest on STEM Talk. I can say with complete confidence that LIGO would not have successfully been constructed without Barry.
And I absolutely look forward to that interview, Ken. Goodbye for now.
Goodbye.
Thank you for listening to STEM Talk. We want this podcast to be discovered by others, so please take a minute to go to iTunes to rate the podcast and perhaps even write a review. More information about this and other episodes can be found at our website, stemtalk.us. There, you can also find more information about the guests we interview.